We present Clutch, a model for generating and captioning 3D hand motions. Given a text description, it can generate a wide variety of 3D natural hand motions, like playing a piano, pouring wine, kneading flour or dough, or given a motion sequence, it produces a concise caption that matches the action and hand rolls. Hands play a central role in daily life, yet modeling natural hand motions remains underexplored. This is due to the fact that most datasets are recorded in studios and have limited scale and variety. Models trained on such data struggle with in-the-wild motion patterns, but scaling studio capture is expensive and slow and time-consuming. To address this, we do the following. Firstly, we introduce 3D Hands in the Wild, a large dataset of hand motion sequences and aligned text descriptions. Secondly, we propose Clutch, an LLM-based hand animation and captioning model with two critical innovations: a novel VQ-VAE architecture to tokenize hand motion coined Shift, and a geometric refinement objective to fine-tune Clutch. In order to train Clutch, we construct a large-scale 3D hand motion dataset from egocentric videos. To this end, we combine VLM with a 3D hand tracker to generate text and 3D motion pairs. However, generating reliable annotations requires a joint reasoning about hand motion, user intent, and object-scene relationships, and naive usage of VLM often will lead to hallucinations. To address this, we propose a novel two-stage annotation pipeline. In Stage 1, we introduce a parallel chain of thought prompting strategy, which decomposes the reasoning process into several specific prompts. The responses are then summarized to produce a high-level description. In Stage 2, we refine these annotations by constraining the VLM to select plausible object-action pairs from a curated vocabulary, mined from EgoVid 5M and Ego 4D narrations. As we see from the result, our two-stage pipeline reduces the hallucinations and produce a better grounded action descriptions. The resulting captions are aligned with the tracked hand motion. Here we present some generated samples from our dataset. The dataset spans broader trajectories and poses than studio data. Now that we have a high-quality dataset, let's design the Clutch model. In order to feed hand motion into the Clutch's LLM, we must first tokenize it. Standard VQ-VAE tokenizers struggle to capture the diversity and complexity of in-the-wild hand motion, often resulting in limited reconstruction quality and generalization. To address this, we introduce our Shift tokenizer. Shift models trajectory and pose components using separate VQ-VAEs, while also disentangling left and right hands during encoding and decoding. Empirically, this formulation achieves stronger generalization and more faithful reconstructions, even under high temporal compression. Using the Shift tokenizer, we can now design Clutch. To repurpose the LLM to predict motion, we first need to add Shift's motion tokens into the LLM's vocabulary. Standard animation-enabled LLMs are trained in two stages: a pre-training stage, where the model learns knowledge about a new domain, and fine-tuning, where the model is refined to a particular task. In both of the stages, the model is trained using next token prediction. While this token-level cross-entropy loss encourages correct next token prediction, it does not guarantee motion fidelity, smoothness, and realism. To address this, we introduce a geometric refinement stage after the pre-training stage. To this end, we adopt a Gumbel softmax parameterization, which enables discrete token selection while directly applying reconstruction loss in hand parameter space. In our experiments, we found that this novel technique improves both motion synthesis and motion captioning performance. The design and training of Clutch is now complete and the model can be trained. Let's look at some results. Given a text prompt, Clutch can generate plausible, high-quality hand motions that are well aligned with the input prompt. Furthermore, given a hand animation, Clutch is capable of producing an accurate captioning of the input motion. Here we ablate how the geometric refinement stage improves the motion quality. Now we show text-to-motion comparison with baselines. Now we show motion-to-text comparison with baselines. This brings us to the end of the video. Clutch makes important progress toward scalable natural 3D hand motion synthesis and captioning. To make Clutch possible, we introduce a novel data annotation pipeline and a dataset built using this pipeline. Clutch is trained with two new innovations: Shift, a part modality decomposed VQ VAE tokenizer for natural hand motion modeling, and a geometric refinement objective used to fine-tune the LLM. Through detailed experiments, we demonstrate that Clutch outperforms the existing methods. Thank you for watching.